In the previous class, we studied Young's experiment, considering the interference between two light waves, two coherent light waves passing through two slits with a small distance separated. Today, in that case, we ignore the width of a single aperture, and that one is treated to be infinitesimally small in comparison with the distance between the two slits. Today, we study starting from the single slit diffraction. We reconsider the Young's experiment, considering finite effect of the aperture diameter. The diffraction by a single slit is the main theme of the starting point of this today's study. Let us first consider the first minimum coming from the diffraction of a single slit. As we have already viewed, when we consider the Huygens principle, diffraction is generated when wave passes through a hole, the slit. It usually radiates, it propagates along the radial direction. And if we increase the width, then the radiation from the propagation of wave through the slit tends to less diffract. Okay, so this is width, and when we construct this resultant waves coming out of a slit of a finite width, we actually combined a list of a set of waves, separate waves that are coherent. And actually this diagram for the wavefronts of the waves coming from this slit is just a superposition. In a similar way, in the previous case for the Young's experiment, we ignore the contribution of all small pieces inside a single slit, treating the contribution to be a single term, and we added the two different phase contribution, electric field E1 and E2 has been added, and considering the phase difference of phi between the two contributions. Today we would like to sum all of the contributions in a single whole by making a lot of pieces and add them all. So in the limit, the n goes to infinity, where n is the number of pieces, then the summation is to be replaced with a definite integral. Before we go ahead, we make a very simple rough calculation to get an idea of what's happening in the interference pattern coming from a single slit. Let us consider two slits, imaginary two slits, hidden in a single slit. This is a single slit of width A. And we divide this one into two pieces, equal pieces. Then it is very similar to the experiment that we have considered. Just with in a rough calculation, the width 1/2 can be treated as a light source, a single light source centered, and another 1/2 of A contribute to the resultant wave, and the two waves, in that case they are separated. This is 1/4 of A, and this is 1/4 of A, quarter. The distance between these two is 1/2 of A. So A is divided into two pieces, and these two pieces are approximated as two single light source, point-like light source, and the separation is just 1/2 of the original aperture. It should be double. This one is A. Okay. In that case, the light coming from the upper one and light coming from the lower one has a separation of 1/2 of D, 1/2 of A. So 1/2 of A is the D in the Young's experiment. So in Young's experiment, two light source, coherent light source, separated by distance D, had a path length difference. This one was a theta. There's a point P that makes an angle of theta. So path length difference was the D sine theta. In here, we, instead of D, we do not have D anymore. The effective D value coming from this case is 1/2 of A. 1/2 of A. So there used to be D sine theta equals something, and D sine theta has a minimum, then is a half integer. First minimum is half integer. Now D is replaced with 1/2 of A. Hence we have the relation for the minimum, the first minimum. Unfortunately, it is not trivial to use this brutal force calculation to find the maximum values. So this is just a starting point, and at the end of the day, we will actually add the whole contribution, dividing a single aperture into many pieces and add them up and find the limit. If the limit exists, the value will be a kind of definite integral, and we will look into the analytic structure of that function. The finding minimum can be extended to the next order, that is the perfect cancellation of the two contribution dividing into a single aperture into two pieces is extended to four pieces. In fact, dividing into many pieces, how many pieces should we divide is relatively obscure. It is a rather subjective, so we do not continue to study this way in detail. But anyway, the simple extension can be made that happen to be it yields the correct answer. Anyhow, that's the reason why the brute force method is usually introduced in most of textbooks. In the third and nth order case can be generalized in the similar manner. The first minimum divided into two pieces, second minimum 4 pieces, third minimum 6 pieces, something like that. So in any case, this cancellation should work. So we keep it as it is and divide it further in each piece into 2 pieces. So that is the next order. And then keep this and divide into 3 pieces each. But it is a rather not easy to explain why we do not extend this one to have every piece into 2 pieces, something like that. So in that case, we divide into 2m. However, in this way, we divide into 2m, and this 2 to the mth power. Okay, so because of this, it's a rather difficult situation to understand what's going on. We had better follow a strict way that respects the basic idea of superposition principle for the wave addition. So, we first review some mathematical tools that we have already developed to study damped harmony oscillators and solving differential equations, and apply the method to study the RLC circuit. The complex number is a very simple, provides us a very simple approach to consider such a rather complicated calculation involving sinusoidal function. The reason is the cosine and sine, its derivative, as we have already seen when we analyzed the RLC circuit, the derivative and the integral of sinusoidal function is a little bit complicated. Eventually it is a regular form, but it's not really simple because there is a sign difference. For example, if we take the derivative of cosine, then derivative of cosine, then you have sine, but we have negative sign on it. Derivative of sine is a plus cosine, something like that. Derivative, double derivative of cosine and double derivative of sine, they have the same style. However, if we introduce exponential I theta, that is cosine theta plus sine theta, the rule for differentiation and integration are very, very simple in comparison with using the pure sinusoidal function. Okay. So complex number, we will learn that any differential equation whose coefficients are linear differential equations whose coefficients are real has its own solution to different, for example, at least the second order differential equation has a two linearly independent solutions. And in our case, Maxwell's equations as well as the equation of motion for RSA circuit and damped harmonic oscillators, they are all second order linear differential equations. And the real solutions, two real solutions can be combined together by, suppose the x and y are two real solutions, then we can multiply I to a single solution and add them up to find that linear combination, which is actually a complex number, is also a solution of that linear differential equation. That's the reason why we can extend the solution for the electric circuit and damped harmonic oscillator and either electric field or magnetic field, that is the solution for the Maxwell's equations. They are all allowed to be expressed as complex numbers. Any complex number is expressed as the sum of two real numbers, x plus I, y, where I is the square root of -1. And then there is a one-to-one correspondence by treating this real and imaginary part of a complex number as the xy coordinate of the two-dimensional Euclidean space. Then r is the radius in the Euclidean space, and that is the square root of x squared plus y squared. That is the modulus of the complex number. And we can define the polar angle theta in the two-dimensional Cartesian coordinate system. Use the same one, and after multiplying I to the I-axis, I is multiplied in here, and that it becomes a complex number. And it behaves like a two-dimensional Euclidean vector. To find the modulus, we need to compute x squared plus y squared. That is x squared minus iy squared. That's the reason why modulus is squared. is expressed as in a factorized form, that is the complex number and its own complex conjugate. And complex conjugate has the opposite sign of the imaginary part. This complex number of unit modulus can always be expressed as a cosine plus I sine theta, and we name it as e to the I theta. Its complex conjugate will be of this form, and real part of this e to the I theta is 1/2 of sum of these, and imaginary part, that is sine, can be obtained from the exponentials. We also need the following mathematical tool. The Lobster's rule is a very useful tool to compute the limit of a rational function when both the numerator and denominator approaches 0 when we want to compute the limit to a certain value. In that case, we can expand f of x, f of a, Taylor series expansion, f prime of a is 2 factorial x minus a squared f double prime of a, something like that. Substituting this one into numerator and denominator, if limit vanishes, is x minus a f prime of a x prime minus a g prime of a x minus a squared f double prime of a, and so on. This has the similar structure in the denominator. So if first order derivative, the first order differential coefficient is not vanishing, then the limit can be computed as this. If both of them vanish, then we can neglect this and consider the second one. Again, in that case, we will lead to double prime over double prime. So in this case, f a g a equals 0. In this case, as well as this, and f prime of a g prime of a equals 0, and so on. We shall find a sinc function that is sine x over x, and we frequently compute the limit x goes to 0. This is a typical function appearing in the diffraction. The value of the numerator vanishes as x goes to 0. Denominator also vanishes as x goes to 0. So we can make a Taylor series expansion of sine, and so on. Then if we substitute this one, we will find x 1/3, x cubed, and so on. So this limit is 1 as x goes to 0. We can make use of this brute force expansion, and we can apply the L'Hopital's rule by taking the derivative. We can apply the derivative of explicit function or implicit form. So the derivative of sine becomes cosine, and denominator is 1, so the limit is 1. So it's quite useful formula. In addition, we will divide the single slit into many pieces, and each contribution has a finite amount of phase shift. So this one has delta phi relative to the first, the second, the third one has delta phi, and so on. And if we make use of complex numbers, these phase differences can be expressed as e to the I phi, I2 phi, e to the I3 delta phi, and so on. So if we want to sum all of the contribution based on the superposition principle, we will obtain something like this. E to the I delta phi equals common ratio, then we would have 1 plus R plus R. This is R. 1 is R to the 0th power, so n minus 1 if this kind of summation is necessary. So we learn how to find the geometric sum in high school. So the result is this, or z to the n minus 1, z minus 1. In the limit n goes to infinity and the modulus is less than 1, then z to the nth power, this one approaches 0. In that case, the infinite sum can be evaluated as 1 over 1 minus c. So what we want to compute is this. Now theta is delta phi, and delta phi is the phase difference between adjacent contributions. So we have a geometric series of n terms. Because we divide an aperture into n pieces. Substituting the common ratio into the formula of geometric sum, what we find is this one. Because right now we are dividing into finite pieces, so n dependence should be kept explicitly. In this computation, we find that this complex number can be expressed as a modulus multiplied by complex phase. So it should be some absolute value multiplied by some phase. We would like to express this complex number in this form, because the overall phase won't contribute at all, or even after the computation, the amplitude square that is related to the intensity of the light, that is proportional to the electric field, and it's a scalar product with the complex conjugate. This constant phase vector will cancel. Only the magnitude will survive in the actual calculation for the intensity. To simplify this expression, we pull out the overall vector 1/2 of phase. The reason is that if we pull this 1/2 of phase, the first term has a phase and the other term has opposite phase. Then it is a subtraction, the difference of a complex number and complex conjugate. So it is related to sine theta. And we note that the sum is between two terms that has phase shifted by theta. We remember when we compute the standing wave sine kx minus omega t sine kx minus omega t plus phi. If there is a phase difference by phi, then what we would have is 2 times the cosine half of phi as an amplitude, and eventually the phase became sine kx minus omega t plus 1/2 of phi. So when we have explicit difference in the phase by phi, then the final result has a physical value, amplitude, and the resultant phase are related to 1/2 of phi instead of phi. So simple calculation leads to this. Here, I e to the I 1/2 of theta, this one is a phase, and 2 times sine 1/2 of theta. This is the modulus, because the absolute value of this is 1. So this is a complex phase factor. In a similar manner, we can simplify the numerator. That is trivial if we substitute n theta into theta in here, because the expressions are exactly the same except that theta is replaced with n theta. So this one can be copied and we replace theta by n theta. As I already stated in here, this is a phase vector. And what we obtain in the denominator and numerator over a factor, including factor of 2, cancel exactly, except for a shift in phase. This is n theta over 2, this is 1/2 of theta, so over phase becomes 1/2 of n minus 1 theta. And the ratio of the modulus, these two moduli has the ratio sine 1/2 n theta over sine theta, sine 1/2 theta. As a result, let us consider this one. Here, this k is nothing to do with kx minus omega t. It is just a dummy index that runs from 0 to n minus 1. And each beam has a gap in phase by delta phi, so we have over a vector e to the I k dot x has been already pulled out, and we do not consider in here because they will eventually cancel the squared amplitude. And again, e to the minus I omega t is common, we factored out. And then phase dependent piece is summed using geometric series formula. And finally, we have made use of this one. Here we have replaced the theta by delta phi. Alright? And time dependent factor is pulled in. Again, this over factor is a complex phase of a total sum, and we do not consider this is the real physical meaning. Finally, the absolute value of that complex number is the ratio of two signs. Notice that there's a phase shift. Okay? Phase shift delta phi per each beam, and there's a delta phi per each beam, and this is n is the total number of beams. Total number of beams. Beam means we have divided a single aperture into n apertures. Alright, this is a sum depending on the number of beams, and actually the sum as we take the limit n goes to infinity, well, what we are interested in is the that limiting value. And actually this is a kind of Riemann sum. When I think you are already familiar with the calculus, so if you are not, you can follow this calculation. So, but I don't want to spend longer time to review the mathematics. Instead, this is what we have already obtained. Now, theta, that is a delta phi in the previous calculation, is phi over n, where n is the number of beams, and phi in here is the phase difference between the starting point and end point of a single aperture. So if you follow this calculation, our calculation of this can be expressed as an integral. And finally, that integral has the very similar structure as we have obtained previously. Okay. The Riemann sum is sum of these bars, the area of these bars. This is a function. The area of a function between the function and the x-axis, and that area can be approximated by dividing this region into many pieces. It's just like a histogram. We have a small bar of tiny width and height is a value of a function, but because it's this width is finite. We have boundary value for xk minus 1 and xk. This is the kth bin, where the initial value begins with x0, and the final value is b's to be xn, and function passes in this way, and we can choose any point in this bin. Therefore, there is uncertainty of the area of this blue region. However, if we slice the whole region into many pieces, this tiny piece of error, some of the errors will reach 0. In that case, the area can be approximated as the sum of these bars. And if we choose the maximum value of the height, then it is the upper sum. And if we choose the minimum value of the height, then it becomes a lower sum. And the upper sum and lower sum reaches a single value, then it is defined to be the definite integral of this function. So Riemann sum is a sum of typical value of a function in a given bin, and this is a width. This is the delta xk is the width of the histogram. The height is this function, and this is xk tilde is a value in this region, in this kth bin. If the sum, if you take the limit n goes to infinity and it reaches its limiting value, then it is defined to be an integral. So the width of the bin is b minus a, that is total width of the interval. If we make n bins, and this b minus a over n is the width, in case we have put every width to be the same. Therefore, we have a phase shift from the end point. This is the width of A, aperture width, here to there. The length difference is A, then phase difference between these 2 points will be some phi in phase space. And we divide into n equal pieces, then we would have the width of this summation, Riemann sum, is phi over n. If we make use of this relation, we can rewrite this summation into this, where f of x is exponential ix. Finally, what we have obtained is this integral. We apply this method to compute the interference pattern due to a single slit diffraction. First, we divide an aperture of width A into n pieces. That delta x for a single partial slit is delta x, and we used the same value for every bin. So this one is total width divided by number of bins, A over M. The path difference between the two endpoints is, we have theta, is A sine theta. So path length difference between the starting point and end point will be, this one will be A sine theta. Path length difference between the two endpoints is A sine theta. If we use this path length difference in units, express this one in units of wavelength, we divide delta L over lambda. Then A over lambda sine theta should be the phase difference, delta phi, between two endpoints of each beam, delta phi. Now, A in the length space, A in the phase space, A to phi, length, phase. In each beam, it becomes A over N. That is the delta x. And here we hover, we have delta phi. Delta phi is A over delta L is total. Delta phi is the total. Here I wrote this delta L to be the total, so the A sine theta, instead of divided by N. Okay, now let us compute the electric field due to the whole contribution coming from the N beams. Here is E1, and second beam E2, and nth beam En. So we sum everything up. However, the electric field due to the wave coming from this small width depends on width, so it is not a finite value, but it is an infinitesimal value that reaches the infinitesimal expression. So if we sum them all, they should be delta, and this delta should be, if we have a certain limiting value, this one is to be expressed as integral of differential electric field. So, in summary, aperture width is A, and coordinate of a point in a slit, this is the 0 and A, we choose a variable real number x to identify the position in a partial aperture. And phase of the partial aperture is depending on the position x, and the phi A is to be A divided by lambda, something like that. Here we choose this one to be 0. And the width, finite width delta x, is replaced with the differential dx. This is the width of dx. And then the electric field generated by this harsher aperture, contribution is dE. We consider the case the screen is very far and the radial effect is just constant, so the amplitude, absolute value of amplitude does not decay very much because we are considering angle, small angle theta, and the case d is very large. Then there is a proportional constant, and the electric field is actually the constant vector. However, it has some phase dependence depending on x that comes from the kx minus omega t. All right. According to our analysis for the Maxwell's equation, electric field is expressed as an amplitude, and amplitude is a vector. We recall that if we combine the Maxwell's equation, it becomes wave equations for E field and B field for both, and every component to satisfy the wave equation. But we remember that electric field, magnetic field, E field, B field, and directional propagation, they make a cyclic triad. And we define the the polarization vector that is on a perpendicular plane that transfers to the propagation direction, so that we choose E as a polarization vector that is independent of x and t, polarization vector. So if we consider that one, what we consider is a kr minus omega t. Here r is a radial vector from the aperture to the screen, point P, but we assume that it's very far and angle is very small, theta is very small, so this vector can be pulled out as a constant for all over our calculation. So what we consider is x dependence of the phase, this phi x. We recall that the beginning point 0 and end point is a, and in this case the phase difference is path length difference is a sine theta, and path length difference will be 0 because it is in comparison with this point. All right. So for simplicity, at the end point we have phi, beginning point 0, or we could choose 1/2 of minus 1/2 phi and plus 1/2 phi for the upper end point. 0 a minus 1/2 phi, 1/2 phi, or 0 and phi. And regarding the overall factor, it is integrated over the length, and we assume that it is a uniform, and the length, the total length is a, so we just use the dx over a. If there is a constant, this dx over a integral is a over a becomes a 1, has the unit normalization. It is something like what we want to do when we compute the electric field generated by a uniform line charge. Now the remaining calculation is quite straightforward. Electric field is the integral of differential, and we have density, uniform density, 1 over A integrated over the whole width, and E0 vector is expressed as some amplitude depending on the radius, and the polarization vector that determines a unit normal direction relative to the propagation of the electromagnetic wave, and common phase vector and relative phase vector. X dependence appears only in the relative phase vector, and this integral can be evaluated from 0 to a, and explicit value of phi of x is 2 pi over lambda x sine theta. This integral can be done explicitly. The final result is like that. So integral is much simpler than the summation that we have derived. Finally, the net electric field at point P, due to a uniform contribution of partial apertures distributed over a whole aperture or whole single aperture, is like that. All right. Therefore, what we have is this function. This is a sinc function. As phi goes to 0, phi means the gap between the two ends of the aperture, the phase difference between the two ends of the single aperture. And when phi goes to 0, means A goes to 0, because phi has the dependence, A sine theta over lambda. As A goes to 0, phi goes to 0. Sure, in units of 2 pi. All right, in units of 2 pi. All right, so this is our final formula. Because this overall factor E0R has not been computed, it can be normalized by the central value. At the central value, phi is 2 pi A over lambda sine theta when theta equals 0. If you substitute theta equals 0, this right side becomes 0, so phi becomes 0. So if you take the limit as the phi goes to 0, then you will get theta goes to 0, you will get phi equals 0. So the ratio of the absolute value of this and the corresponding value at theta equals 0 do not have any other factor except for this sinc function. Sinc function has a shape usually in this form, but it depends on the parameter. We know 1/2 of phi is because of phi is scaled with 2 pi a over lambda sine theta. 1/2 pi is pi a over a sine theta. We can find the minimum values, and by taking the derivative, we can find the value at which the amplitude, this one, becomes maximum value. So minimum and maximum, minimum and maximum. Finding a minimum value is trivial because the numerator becomes 0. At phi equals 0, it never becomes 0 because of the denominator, except that every point where numerator vanishes, we have exact 0 in the intensity plot. In here, the shape of their curves are depending on the magnitude of A relative to the wavelengths. This is the key factor, A over lambda. If A is large enough, we can see the tails of the wavy lines. If A is of order of wavelengths or even smaller, then it becomes flatter and flatter. So wavy structure appears when the wavelength is shorter, or for a given wavelength, when the aperture becomes larger and larger, then the width of this sinc function shrinks to a small space. The explicit computation to find out the minimum and maximum values are described in here in detail. You can follow up. In the case of aperture whose shape is a circular form, the minimum structure, the basic structure of wavy, the diffraction pattern is similar, but the numerical value for the minimum values are rather different from the case that we have considered. Our case is just a simple case. Slits are very long and diffraction pattern appears uniformly, just like a standing wave. However, if the aperture is circular, then wavy lines is not a one dimension, but it is distributed in 2 dimensions as a concentric circle. The mathematical approach to compute this is rather tedious, and you can learn about it if you study mathematical physics. But we just to quote the result, that is a Bessel function. This formula is called the area intensity pattern. There are various kinds of Bessel function, but this J is a first kind. The numerical values for first 0, second 0, third 0, first 0. It is in fact just like the sinc function. At the central part, the intensity is maximized. But the first minimum value is related to numerical value. This one is related to the first zero of the Bessel function G1. So 1.22 is originated from these numerical values. resolvability. If two images are very close, any light does diffract. So any light source generate on the screen, a point source generate a finite width of image. In this case, the image is very, very wide, and we have a rather narrow image. But in case we have two images overlap, if they are very close, too close, then we cannot identify the left and right separately. This is marginally separated. These two images are well separated to identify. So resolvability is related to the fact whether we can determine the actual different images are originating from different source or single source. Although they are produced differently, observation does not say they are identifiable. So resolving power is a rather interesting, useful tool to identify the analysis of image. So usually the source is a point source. In that case, rather than using the sinc function analysis, we use the Bessel function analysis for the circular aperture style to find out the criterion for the resolvability. This is the repeated calculation, so I don't want to repeat again. However, this part is an application to double-slit experiment. Intensity formula of a double-slit experiment. We have computed the single-slit case that has a factor of sinc function. In the case of double-slit, we do the same job, but we have two apertures of width A and A, so normalization factor is 2A because the area is A and A, 2A. And the phase difference between these 2 points was 0 and 5, and we have additional scale. That is the phase difference between these two. We use thick phi. And this thick phi in the distance scale, it is related to the d, that is the distance between the two apertures. If you follow this detailed calculation, what you will find is the same factor that we have obtained for a single aperture. In addition, we have additional factor that is the usual factor coming from the addition of two sines, the cosine of half of phi. Again, when the angle theta equals to 0, the limiting value of the whole factor is normalized to be 1. So Young's experiment can be analyzed again with the formula, explicit formula of integration. We have a single slit over a factor multiplied by cosine square, where cosine square has a phase factor. The phase depends on the d, the gap between the two apertures, and small phi has a dependence of a, that is the width of a single slit. Because d and a are independent, and this integral and this integral, they are common for the overall factor, the phase difference of the two contributions appears as a cosine squared to 1/2 of phi, that capital phi is depending on D instead of A. Because of this, our original pattern for the single slit experiment is like that, sinc function, where the middle peak is very steep, middle peak is very high relative to next one, and then decays. We have additional factor that is going up and down. What we know is phi is greater than small phi. You know, sine x and sine tan x. Tan x is very small wavelength. It repeats many times. So if you multiply sine x times the sine tan x, then your final answer will be you have this sine, however, inside you have wavy sides. We call this one to be envelope. Alright, so as a result, we have a large structure. This is a large structure. This is a short structure. I mean, the D is large scale, but for a large scale, the wavy line has the very small gap. This is related to a tiny parameter A. It is revealed as an interference pattern as a wide range because of diffraction. As a result, we have this kind of form. If you carry out a single slit experiment, it depends on A. And relative to lambda, the width of this curve changes depending on, so this is small a in comparison with lambda, in units of lambda. When a is small, the width is large. Anyway, if a is fixed and then D is introduced, D is much bigger than A, then wavy lines, wavy curves appears inside this envelope. This is the result of the double slit experiment when D is very large in comparison with A. In case A is very small, A becomes very small, this curve will be almost flat. Because of that, even though only the first envelope appears as this whole distribution, all of the amplitude becomes very similar. This is a double slit experiment when A is very small, the D is still very large. So this is the typical structure of the interference pattern coming from the double slit experiment, considering both the distance and the finite aperture size of a single aperture. All right. In our calculation, we have made use of the summation for geometric series, quite useful geometric series. But this technique can also be applied to find out whether unobvious formula for the summation of finite sum of signs. And if you can do this calculation by making use of the complex analysis, then what you can take the limit as n goes to infinity and use the width 1 over n times something, then you can replace this one as you can take the limit to n goes to infinity to find out this one is eventually expressed as an integral for the product of signs. And this expression is very, very important for the quantum mechanics bound state calculation. That's it for today.